So let's jump right into it. Radio astronomy typically involves big apertures, and by that I mean big antennas. And that's no surprise to anyone. You all know what the big telescopes look like. They're gigantic dishes. Not the only way to do it, but this is a vast, very large fraction of what instrumentation is used. And we can characterize large apertures in terms of a pattern. Here's the classic sync-like pattern that you get from a big aperture. No surprise that the half-power beam width, or you could call it the full width at half maximum, or whatever your favorite term is to characterize the width of a main lobe, is something like wavelength over the diameter, if it's a circular thing, or the aperture in general. That's in radians, of course. We talk about the gain of an antenna as being 4 pi over lambda squared, lambda being wavelength, times the collecting area. The collecting area being the physical aperture, so pi d over 2 squared for a circle, for a circular aperture, times an effective aperture, which or a aperture efficiency, which describes how well or what fraction of the effective aperture in terms of determining gain is actually used. And here D is diameter, but D can be really anything that describes the overall dimension of the thing which is creating the pattern. Typically, big dishes in radio astronomy are under-illuminated. They're under-illuminated for a whole bunch of reasons. So the first side lobe tends to be down somewhere in the 20 to 30 dB range. So if you're interested in side lobe levels, this is your slide. They're under-illuminated primarily because you want to minimize spillover. Spillover means an increase in system temperature, which is typically bad. Having low side lobes is useful for other reasons. I should point out here that the radiometric definition of gain, which astronomers are inclined to use, is actually different. Radiometric gain is still proportional to the collecting area, but has units of Kelvin per Jansky, and this can lead to confusion. I recall the first time I went to Green Bank and getting a tour from a postdoc, and someone asked what the gain of the GBT was, and the student said, or the postdoc said, it's huge, it's 2. To which I kind of scratched my head and said, well, it's like a dipole? No, it's 2 kelvins per Jansky. 2 kelvins per Jansky is enormous. So it's just be aware of that. The side lobes for these apertures are very, very poorly known. I've got another slide on that in a moment, but you should know this, and they're probably variable. So if you're interested in doing interference analysis, know this, that there is some understanding of what the close-in side lobes might be doing. But once you get out to 3rd, 4th, 5th, nth side lobe, forget it. And I'll also tell you that they're probably not around 0 dBi or so. Next slide. The far out side lobes are extremely difficult to know. Just to give you one example, which is I happen to know of, this is the 76-meter dish at Manchester, in the UK. And this is a plot of side lobe measurements off axis. So it's a very big dish, so it's got a very narrow main beam. So if you look out here, see angles out to 90 degrees. You see the measurements of the dots, and you see the spillover here, by the way. So even with some under illumination, the spillover is considerable. These markers should tell you how hard it is to get those measurements. So this is really more of a statistical description of what's going on out there as opposed to a deterministic plot of side lobes. And as a result, there's these side lobe models. Here's one that's commonly used. There's another one which I couldn't summon up in the time I had to make this. There's at least 2 prominent side lobe models. They both assume something like -10 dBi, dB relative to isotropic, over a big chunk, far below 0 dBi, just to be clear, and then some envelope. And that envelope normally accounts for this 1 over n roll off over here. It normally accounts for some spillover, although you see the models are never quite right. They'll fit more or less different dishes, better or worse. So you should be aware of this. I think it's fairly fair to say that 0 dBi for far outside lobes is conservative. They're certainly much less than that. -10 dBi is probably a risky thing to use, especially when you have spillover. And for more complicated optical systems, there's diffraction from support systems and all that. So this is kind of what you're dealing with. Okay, so now radiometry. We've got a big dish. We're capturing signals. We want to know what to do with them. The concepts are very similar to what Joel showed this morning. The analysis I have here is essentially the same, but we use somewhat different terminology, and we kind of enumerate things in a different way. But let me go ahead and do it. So we're on the same sheet of music. You can think of the flux arriving at a telescope. We typically characterize this as a power flux or a spectral power flux density. All these terms mean basically the same thing. The units tell you what we're actually looking at: watts per square meter per hertz. That is the usual characterization. And because these numbers are so small, it's convenient to assign a unit, which is a order of magnitude, many orders of magnitude less than that. One Jansky being 10 to the minus 26 watts per square meter per hertz. So when I say Jansky, I'm just talking about this: watts per square meter per hertz divided by 10 to the minus 26. Or, excuse me, divided by 10 to the minus 26. So what does the dish see? Well, the dish sees that incident flux times the effective aperture. That gives you watts per hertz. In other words, power spectral density. This 1/2 is a point of confusion, especially when you're dealing with engineers and astronomers in the same room. Typically, the astronomical flux is roughly uniformly distributed in both polarizations, being noise-like in polarization as well as in everything else. So astronomers typically report this as the flux in both polarizations. Of course, you can only see one polarization at a time using one feed. So what you get out of one feed is 1/2 of S. So just be aware of that. Here's a receiver. Receiver has gain G, bandwidth B. So what you measure from such a thing is the total power, which is 1/2 flux times effective aperture, times the gain, times the bandwidth, and now you have watts. And then I will cavalierly dismiss everything else that happens in the telescope as being a detector. More on that later. We're interested in signal and noise, so of course we have to characterize the noise. The noise that Joel introduced you to this morning, primarily the receiver noise, is down here. For radio astronomy receivers of the top tier variety anyways, they're typically characterized as having noise temperatures on the order of 10K to 50K. That's input referred. So what we mean by that is that you can describe the output power of such a thing just due to the internal noise as being Boltzmann's constant, 1.38 times 10 to the minus 23rd joules per Kelvin, times that temperature that we've used to characterize the noisiness of the receiver, times gain, times bandwidth once again. And that's that. Of course, the other thing we have to be aware of is, especially for the weakness of the signals that we're interested in here, there is everything else that the telescope picks up, which is not your signal of interest. As Joel explained, we also describe this in terms of an intended temperature, which causes a lot of confusion because it's Kelvin. But what it really is simply a way of describing the power spectral density at the output of the dish as watts per square meter, watts per hertz. All you do is you take watts per hertz, divide by Boltzmann's constant, you get temperature, and that's the temperature we're referring to. So this is the noise incident from all directions expressed as the power spectral density at the output of the dish, or whatever aperture you're using. This number can be anything. I'll show you, maybe I'll show you more about this, maybe I won't. In the range of 1 to 50 gigahertz, it's probably somewhere between 5 Kelvin and 20 Kelvin would be typical numbers. Below 1 gigahertz, it explodes, gets very large. Above 50 gigahertz, of course, you hit atmospheric absorption, things like that, which drive it up for a different reason. These are typical numbers. And then, of course, you see that as a power which the detector gets to see. So that we get the radiometer equation. I can't remember if Joel called it this, but this is what I'll call it. The signal noise ratio that you can measure then is the ratio of power to what you get from the antenna in terms of noise, not signal, plus the noise from the receiver. Simply substituting expressions here, and you get 1 over 2K times AE over T cis times the flux. So what you see here in the box, AE over T-cis, is one way of describing sensitivity. I call it the intrinsic sensitivity. I don't know if anybody else calls it that, but it is a characterization of the sensitivity of the instrument. So an instrument will have this. It's kind of hard for that. That is an irreducible number, and it's convenient to know. It's directly analogous to what a satellite communications engineer would use, G over T, right? So G over T is essentially the same thing, except instead of expressing it in terms of gain, antenna gain, that's directivity over temperature, we're talking about collecting area over temperature. That T-cis is simply a combination of antenna temperature and receiver temperature. So without surprise here, the system temperature is between 150 gigahertz, vary a lot, but again, for top tier, well-engineered systems, they tend to be between 20 Kelvin and 70 Kelvin would be typical numbers. Of course, the question becomes, how long did it take for you to achieve the signal to noise ratio, right? It's just, I did this in terms of powers. Power is time average power in this case. Must have taken some amount of time to get that measurement. And as Joel explained, here's my version of that. It took you 1 over B, right? So the significance of the receiver bandwidth here, or the bandwidth with which you're doing this measurement, is that it also determines the natural time for that the signal noise ratio given by the radiometer equation, what time that refers to. So it's 1 over B. Of course, you can improve the signal noise ratio by averaging for longer. And the way you account for that is by tacking on this factor of B tau to the square 1/2, square root of B tau. I didn't have a square root symbol handy in this particular editor, so it's B tau to the 1/2. So you see for the natural time, it's 1. And for any time longer than 1 over bandwidth, you get an improvement in signal noise ratio. Nothing surprising there. Always useful to see numbers just so you can kind of comprehend what numbers are commonly appear here. So I threw in a GBT example. So here's my eye candy, the GBT. Here's a unimpressively mediocre source in terms of not very strong, not very weak. 0.1 Jansky. I say it's unresolved here. That means it exists entirely within the main lobe. GBT is roughly 110 meters diameter. It's actually an oval, so it doesn't have one diameter, but it's about 110 meters. For the purpose of this, it's good enough. About 70% efficiency. Again, a lot of that is just under illumination for good reason. So you get an effective aperture of 5,500 meters squared. T-cis, about 30 Kelvin would be a typical number. So you get for an AE over T-cis, 183 meters squared per Kelvin. So for the radiometer equation for this particular source, you get a miserable signal noise ratio, 0.007, which you cannot do anything with. So the technique comes in. So you get a benefit from how you do this observation. For example, if you're doing 1.5 kilohertz wide channels and you integrate for 1,000 seconds, that goes up to 8.1. 8.1 would be enough to detect, I would say. That'd be enough to tell you that you saw something there which was significantly different from noise. Probably not good enough for doing measurements of other kinds, but so this is kind of mediocre. But you know, if you want to drive that up to 80, you're going to have to observe for 100 times longer. So 100 times 1,000 seconds is many hours. So now you start to appreciate the what telescopes have to put up with. You might argue about the bandwidth here. There are many bandwidths which are relevant, and this is what's going to get confusing in this presentation. The bandwidth of the receiver front end is probably hundreds of megahertz to gigahertz wide, but we always break that up into small chunks. For example, if we're doing spectroscopy, we want to know the spectral shape of something, and that might be varying over kilohertz. So if we're interested in seeing those changes, we are really the relevant bandwidth is a small fraction of the passband. So in this case, I'm using 1.5 kilohertz, which would be a relatively common kind of number to use. Kilohertz, hundreds of kilohertz in some cases, larger channel bandwidths at higher frequencies. But the idea is that this is a small fraction of the bandwidth available. For the GBT, here is a nice plot that is provided by those folks of their system temperature. Again, this is receiver temperature plus antenna temperature. And I talked about 1 to 50 gigahertz, which is in here, which is kind of the sweet spot, right? And I said lower temperatures, you have to deal with a couple of things. The galactic synchrotron background is 1. That drives temperatures up over here. And then there's all the stuff you know about atmospheric absorption, et cetera, that drives system temperatures up over here. I should point out that this is, even though it's for the GBT, this really is the same for just about any well-engineered instrument, regardless of size. The reason is this is not dependent on the collecting area. And you also see here all the receivers that the GBT has available to it, quite a few, and you see they cover most of the range here. I will keep coming back to that idea, but I want to just introduce in this slide the fact that there are receivers covering much of the spectrum, nearly all the spectrum, between about 300 megahertz up to 100 gigahertz or so. So B and tau limit sensitivity. They limit the ultimate sensitivity to observation. You might wonder what limits B. Well, there are a couple things. The source. So there are a whole bunch of different sources that get observed. There are spectral lines. Here's an example of a spectral line. Doesn't look like one line. It's smeared all over the place, and that's why they're interesting. Is that smearing of a narrowband emission tells you things about how fast it's moving. So this is what spectral line observations often look like. So if the energy is all limited to within a few hundred kilohertz, then that's going to be the ultimate bandwidth for detection. If you're just interested in what the variation is here, well, then you're going to have to do, B is going to become whatever it takes for you to resolve the shape of this thing. That would be more like kilohertz. We also have things called continuum sources, which I'll come back to. Continuum sources are things which emit significant flux at all frequencies in the radio spectrum. So over here is an example of a continuum source. You see we're going from 1 gigahertz to well beyond 100 gigahertz. In fact, it goes down here too. It's just not plotted. You could really measure it anywhere, but where you measure it is going to tell you something about just that part of the spectrum. So yes, you could increase the bandwidth. You could measure this with 100 megahertz bandwidth, say, but as the bandwidth increased, you'd start to lose the ability to know what the spectrum looks like, whether it's going down, whether it's going up, or so on. So that becomes a limitation on B. There's, of course, technology. It's going to limit B, but although these days, that's really not a limit. I think telescopes now routinely swallow gigahertz of spectrum at a time, and that is not the limitation it used to be. What is a limitation is interference, and that comes in 2 flavors. You may or may not be able to tolerate interference within the passband. So you may have to have a passband which, to your ability to determine, is clear of interference. That might limit where you can observe and how wide a bandwidth you can use. Of course, you may not be able to tolerate interference near the passband if you're linearity limited, if the filtering is not sufficient. These 2 things together may limit the range available to you to observe, even if you're looking at an object that's emitting across the entire radio spectrum. Then you could consider all the things that limit integration time, and there are a few. Once again, they're the source. I find often among my engineering colleagues that they do not realize that radio sources can be dynamic. They are not fixed. In fact, many of the most interesting ones, maybe even most, are not fixed in any particular way. They're dynamic. The poster child for this is fast radio bursts, which you can only see at millisecond. They're 1 millisecond, events which are milliseconds long. They happen once and you're done. So the integration time is limited to a millisecond. Pulsars are kind of funny animals. They can be from nanoseconds to days. The periodic emission can be observed, doesn't really change that much, but the anomalous things that pulsars do can occur in very short time frames and be one-off events. There are also all kinds of things which are not pulsars, but the way you observe pulsars through the interstellar medium lead to scintillation effects, and those can result in flux changes over days, for example, that can be interesting and scientifically relevant. There are things known as intraday variables, sources which intrinsically vary over hours or days. So, that limits the integration time. By the way, talking about a day of integration is not a ridiculous idea. There are many examples where, again, I can't say how common it is, but it is quite common to have to integrate for, tens, hundreds, thousands of hours before you're done. So there's a whole range of possibilities here. The other thing that limits integration time is stability. And now, as an engineer, I'm forced to discriminate between what an RF engineer thinks of stability and versus what a radiometer person thinks of as stability. Here I'm talking about radiometric stability, just to be clear. And that is the fact that the conditions under which you're measuring power are not stationary. So one common problem is receiver gain variations with temperature. You can never hold the temperature constant enough. And to the extent that the temperature of the receiver is going up and down, I'm talking about the physical temperature, the gain will change. And that becomes now something which confuses the measurement. So a picture that would be helpful here is to look at essentially signal noise ratio here as a function of time. It's log, so it goes down by this factor of 1/2 here, corresponding to the square root of b tau. And in principle, you should be able to ride this curve down for as long as you want. And every once in a while, people can do this. They can get very, very far down here. Again, maybe days. But what quite often happens is eventually you hit something which is not stationary anymore, and all of a sudden the curve is doing this. It's getting worse. So receiver gain variations would be one way to do that. It's essentially, sure, you can calibrate, you can repeat that calibration over time, but at some point you eventually hit the point where you just can't track that gain variation good enough relative to the sensitivity you've achieved, and you bottom out here and you take off again. Experiment conditions. These are things like the dish slewing around and dragging a side lobe, say going from the sky to the ground. That will cause a change in the system temperature, and all of a sudden you're wiggling around down here. And then, of course, there's interference. This is, to be honest, one of the most poorly known, poorly understood things that happen to radio astronomers, and probably has an outsized importance. I always kind of feel bad that we don't spend more time trying to figure this out. But there are noise floors, and those noise floors can be attributed to interference. And eventually you hit them, and you hit them at different levels, different conditions, different frequencies, different times of day. They're different. They're kind of a subtle and complex effect. And that can be the thing which ultimately causes you to hit the bottom here and take off again. So these are all, and I'm talking about diffuse interference here, not things which are immediately apparent, but things which only show up after you've been integrating for a very long time. I'll talk about imaging later, but when we talk about imaging systems, we have an issue known as confusion noise. And this is when you're making images, it turns out that at some point, the sensitivity to image is limited by the fact that there's the rest of the universe is coming in through the side lobes of the interferometer, and that becomes a non-stationary contribution here. So this either levels out or starts taking off again. Again, this is astronomy. This is nothing terrestrial causing this. This is the astronomy causing this. It's just something that can only be fixed by changing the design of the instrument. Or improve this thing. You can never fix it. You can just make it better. The key point here is there's always, I should say often, there's always an optimal integration time, and it's often shorter than what you'd want for the sensitivity that you think you'd have or deserve. And the optimal integration time is, of course, where this curve takes off. So that's the story there. So as a result, the required b tau, the required sensitivity that's contributed by the technique of observing, is always greater than the effective b tau. There's, you can see this right away. For example, people often forget that detectors don't measure signal to noise ratio. Detectors measure power. So if you want to measure signal to noise ratio, you have to do two measurements. You have to measure signal plus noise and then noise. So, to first order, this doubles the amount of time you need because you have to do two different measurements, presumably with the same integration time. How do you get the end measurement? Well, if you're doing spectral line work, you can look beyond the spectral line and hope that that area in the spectrum beyond the spectral line is otherwise empty. It's just an expression of the system temperature. That can backfire, but often works. Or you can slew the dish somewhere else in the sky where you think the source isn't. Again, this can backfire, but it is important technique. It's frequently used, but it vastly increases the time required to complete the observation because big telescopes, no surprise, move slowly because they're big. So this can increase the amount of time, wall clock time, it takes to achieve a certain integration time. And then, of course, I should point out here, you should not confuse detection with measurement of absolute flux with the accurate measurement of absolute flux. You know, if you just want to detect something, you just want to know the signal noise ratio is greater than some number. If you actually want to know what that number is, in other words, how many watts per square meter per hertz, you have to do a calibration. Now calibration is contributing to the time, that's the wall clock time that takes to make the observation. And if you want an accurate estimation, then of course you're looking for these orders of magnitude increase in the signal noise ratio. Every order of magnitude increase in the signal noise ratio is a factor of 100 in terms of either B or tau. If you're doing spectral line work, that's all tau. If you're doing continuum work, it's probably also at least some of the tau, somewhat going to have to be tau, because eventually you end up being bounded by some chunk of spectrum that you can't observe in productively, perhaps because of interference. Bottom line here is the required B tau is always much greater than what you need just to get the SNR that is anticipated through the radiometer equation. So the sensitivity of the receivers, part of the answer to the top level question. Let's just throw out some numbers here. Engineers like noise figure. If you work in this area long enough, you become ambidextrous. You can think equally well in terms of noise figure or temperature. So I think I have deconvolved that in my presentation here, but I may slide from one to the other. In terms of noise figure, typical receiver noise temperature of 20K, that would be about 0.3 dB, right, noise figure. To get there, you typically have to cool the receiver. Keep in mind, we're not talking about just one amplifier here. We're talking about the stuff that determines the overall noise figure. So we're not talking about just perhaps one LNA. You're talking about a chunk of RF plumbing that collectively determines this noise figure. When we say cooling, that is an understatement. Typically, that thing is frozen hard. 20 Kelvin physical temperature would not be an unusual number to cool that thing down to. The advantages are pretty clear. For example, if you have a set of RF plumbing, which has an input referred resistive attenuation of 2 dB, such that the noise figure is above 2 dB. I'm trying to come up with a limiting argument here. If you have 2 dB of input referred resistive attenuation, the noise figure has to be at least 2 dB. The gain is 0.63 in linear units. At room temperature, which is about 293 Kelvin, I think that's 68 degrees Fahrenheit, the contribution to the receiver temperature would be 100 Kelvin. You already see that's ridiculous. It's absurd. That's much greater than the 30 Kelvin or so that I'm talking about in previous slides. That is not something we would consider putting in the focus room of a $100 million telescope. We want to cool that down to, say, 20 Kelvin. Now that contribution became 7K. Now that's a reasonable number. It's comparable to the intended temperature. Going down much lower, limited benefit because the intended temperature then will become the dominating thing. But the point of this is to demonstrate even small increases in the receiver temperature, I'm talking about the radiometric temperature, are very painful. So for example, consider receiver temperature plus antenna temperature equals system temperature here. That's 20K plus 10K is 30K, just to, again, use round numbers. If you increase the receiver temperature to 30K, which is super easy to do, that could be a bad connection, frankly. And so it's very easy to end up at 30K. Well, that increases the system temperature to 40K. The A over T sys, the intrinsic sensitivity of the instrument, goes down by 25%. That's already horrifying. But if you think in terms of the sensitivity that's now has to the technique now has to make up for, that's got to go up by 78%. So if you're doing an integration of hours or tens of hours or days, that 78% increase in integration time is horrifying. It's just logistically intractable. So there is a very strong incentive to keep these things as cool as you can, or as low a system temperature as you can possibly accomplish. And there's consequences here. So I know, especially in this particular audience, there are probably many people really interested in filtering and really enthusiastic about putting filters, additional filters and things. That's really hard to do for some of these instruments. It's not that people don't want to do it, and it's not really that it would help with linearity, for example. But the problem is that you need an extraordinarily low insertion loss, where the insertion loss now I'm talking about that due to dissipative losses, has to be very, very low not to significantly increase the receiver temperature. So having really sharp filters is difficult. That makes telescopes vulnerable to out-of-band interference. It's a trade-off that we have learned to live with, and altering that trade point and the trade-off is requires a lot of agonizing, a lot of gnashing of teeth, and is not a simple thing to do.